Last week we talked about three-phase AC voltage, and now we're going to talk about how voltage is actually generated. Um, there are many different ways we can come up with energy to create electricity. So there's not just one way, of course, everyone knows there's many ways. Um, there are hydroelectric dams. That's one way that energy is created. There are geothermal power plants where they take actually heat from the earth and create some kind of energy. There are photovoltaic arrays, which is basically a type of solar power plant. It's not the only type of solar power, but it is a type of solar power. There are wind turbines. There are also nuclear power plants. This is a newer one, but there are different nuclear power plants. There aren't so many in Japan anymore after the tsunami, but they certainly are a good source of energy. There are solar thermal plants, which is actually a different kind of solar plant where there's actually a heating mechanism going on that is creating energy. There are natural gas power stations that take natural gas and turn it into electricity. And there are also biomass power plants, which basically burn trash. That's what they are, actually waste incinerators, and they use that to create electricity. So there are plenty of ways that electricity is generated. Everything pretty much that is produced, not everything, mostly, the energy is used to create steam, and the steam drives turbines. The types of station that use turbines are coal, nuclear, geothermal, waste incineration, solar thermal, and most natural gas plants. Plants that don't use steam would be hydroelectric because, of course, the motion of water actually creates turning, so they don't need to do that. And then some natural gas plants and others that use diesel don't do that. And then the photovoltaic type of solar and plants and wind turbines also don't use steam. But most power plants actually do use steam. And a generator takes that mechanical energy and converts it to electrical energy. So the steam basically gives us some mechanical energy, and then it's converted by a generator into electrical. So three-phase generators are pretty much the source of all the electrical energy that's distributed around. Generators have two parts. They have the stator, which is stationary, and the rotor, which rotates. This is a actually kind of old generator that system in a power plant somewhere. I can't remember where, but you can see that this is actually the stator part, and rotor that turns in the middle, and it generates electricity. The stator is wound with coils that are 120 degrees apart, which kind of makes sense since three-phase voltage always differs by 120 degrees. And the core of the stator is laminated to reduce losses. The rotor spins inside the stator, and it creates a magnetic field. And the magnetic field it creates induces current in the coils of the stator. Each coil produces one phase of AC voltage. Also, each coil has a magnetic field because it has current in it. So each coil has a north and a south pole. We call those armature windings. There is often some, not confusion, but just inconsistency of how armature windings compare to are used as far as motors and generators and that kind of thing. But the general idea is that the armature is connected to the part of the output, and then other windings are connected to the input. So this is a stator. It has coils, and it looks like all one coil, and it's really not. It's actually several coils. They're interconnected, and it depends on the rotor that goes in it how many actual different coils we have. But then there's laminations around the inside to reduce losses. And this is a big stator, and you can see a little better how the coils are connected and how the lamination works, and you can see this is relatively large. But in the rotor now, the rotor has a DC field winding that produces a current, an excitation current. And it requires that to sort of get everything going. As the rotor spins, the current in the field winding, that's where the magnetic field comes from. If the rotor spins inside the stator, which it does, the magnetic field, again, induces current in the stator coils, and the field winding also has a north and south pole, just like the armature winding. So there's actually a magnetic field associated with the stator and a magnetic field associated with the rotor. In a generator, especially in a synchronous generator, those magnetic fields are the same. In other devices, as you'll see later, those magnetic fields aren't necessarily lined up. But in this example, they will be, and they are. This is actually a whole generator. It can actually also be used as a motor. Generators and motors are actually, for the most part, the same thing. We're just looking at the electricity producing part, where the rotor has been removed, and you can see the stator, and you can actually see connections up here, which could be used to produce voltage. They could also be used to apply voltage and create magnetic power, but we'll get there later. And you can see on this diagram, these are the DC field windings inside the rotor. This is actually a device that was in one of our labs, so this is actually on campus here. And one of the questions I always had as a student is, if the windings are here and the rotor's moving, how is are the windings like connected to anything? Because would seem like the wires would just go round and round and round and get all tangled up. But this is what happens. There are spinning contacts, and those spinning contacts are what power the excitation winding, or the DC winding in the rotor. So these are always connected, and the rotor can spin and still remain connected to this DC voltage. You see there's one potential here and another potential there, and then that provides a potential difference that gets current going inside the rotor. So this is kind of just a video, this is from our lab, of how the actual generator works. It's very short. This is the synchronous motor, and that's the excitation field. And we can start it running. You can actually hear the generator running now. We turn up the excitation field, and we get more voltage, not a lot more, just a little bit more. But if we turn up the RPMs, we get a lot more voltage and a higher frequency. So that's basically very short, brief explanation of how the voltage is generated. And the mechanical power that's coming into a generator, and this is where we get into the more mathematical part of this lecture. The mechanical power applies torque as it turns the rotor. You guys as mechanical engineers are all into torque, I know, so this is your chance. The torque is related to the force applied in the distance, which most people learn about in physics, and the mechanical power produced just depends on the applied torque and the speed of the rotor. And we have an equation we use that has a conversion here, and if you did not have your torque in Newton meters but rather in foot-pounds, and you had your power in horsepower, you would have a different conversion. But since this is technically an electrical course, we're just going to talk about watts, and we're not going to talk about horsepower, but you could. So as the rotor turns, we get a changing voltage. And the voltage actually depends on how fast the rotor is going, and then something known as the generating constant. And the generating constant will be given, so you don't need to worry about so much about where that comes from. But the voltage generated is just equal to the generating constant times the speed. So as you saw in the video, as you increase the speed, you directly increase the voltage. The frequency also depends on the speed, as you can see in the video, but it also depends on the number of poles in the generator. Anytime you have a coil, you have some kind of magnetic field, you're going to have a north and a south pole. If the rotor has only one north and one south, that is a two-pole system. If it has sets of windings such that you actually have more than two, since poles are always in pairs, you could have, say, four, where you had two norths and two souths. That would be a four-pole generator. And changing the number of poles means that for a given frequency, you don't have to run it as fast. So a two-pole generator would have to run twice as fast as a four-pole generator to provide the same frequency. So if we run it at, say, a two-pole generator at 3,600 RPM, we can get 60 hertz. 60 hertz is generally what we would want. Then if we change it and have two sets of three windings and the four-pole generator, you can see that you only run half as much. So that's always a good thing. There is a trade-off with expense and all that, but adding poles generally makes it a little bit easier to generate the frequency that you want. Mechanical power applied to the rotor, some of it's lost, obviously. You have some windings and friction and all that, and we call those rotational losses. As the rotor rotates, the magnetic poles are going to switch back and forth. And when that happens, the north pole of the rotor and the north pole of the stator actually have a little bit of opposition as they're running. And this actually creates something known as counter torque. It's kind of a loss. The counter torque is related to how strong the rotor and magnetic fields are, and we just use a constant K sub T to describe the interaction between the two. And the torque, or the counter torque, is equal to the value of the generating, or the constant, times the armature current. And if you know what the armature current is, you can certainly calculate what the counter torque might be. The armature current would be the phase current in the stator windings. So we've talked about how to calculate line current and phase current depending on if you have a delta or Y connection. That would be the actual current in the windings of the stator. So in a generator, the armature current is the phase current in the actual windings that we have. The mechanical power that you apply to a generator has to be strong enough to overcome the losses, so both the rotational losses and the counter torque. So that needs to be greater than those two in order to actually start spinning. The wire in armature coils also has some resistance. And so what we do is we actually find the current in that wire. There doesn't have any real voltage across it we can measure. We can certainly measure the current. And when you square the current times that resistance, that gives you the power loss due to the resistance of the wire. And we call that copper loss because, in general, of course, the windings are made of copper. There are some stray losses also due to manufacturing and design defects, and all of these together really still allow about 85 to 90% of the mechanical power applied to a generator to be delivered as actual electrical power. So let's look at an example. We have a generator with a torque constant of 0.5 newton meters per amp, and the load voltage is 50 volts and the load power is 800 watts. We want to determine the counter torque and how fast the generator is going. So first we can calculate the armature current. Remember, the armature current is the current in the stator windings, and the stator is actually the load because we're generating voltage. So the voltage that is being produced in this case would be 50 volts, and the power that is being output would be 800 watts. So we can figure out the armature current by just taking the power and dividing by the voltage, and we get 16 amps for the amount of current going through the armature. The counter torque is just the torque constant times the armature current, so we get 0.5 times 16, which gives us 8 newton meters. And then remember that power is equal to the speed times the torque over 9.55, so the speed is going to be 9.55 times the power over the torque, which gives us 955 RPM.